This is day 3 of section 14.1. We're going to be using mathematical induction to prove a statement about factors. So this will be the last type of problem that we look at for mathematical induction. So here's our statement. We're going to use mathematical induction to show that 23 to the n minus 1 is divisible by 11. So we're going to use our same steps. We're going to have our base step. And in our base step, we will show that p of 1 is true. So 23 to the first power minus 1 is equal to 23 minus 1, which is 22, and this is divisible by 11. So that holds true. Now for our inductive step, we are going to assume that p of k is true, and we want to show that p of k plus 1 is true. So now what we have to do is be able to write this statement here as an equation. So this is the trickier part, not so much tricky I guess, but what you need to know in order to set this up. So p of k, this statement, can be written as 11 times some whole number is equal to 23 to the k minus 1. So this is showing that this is divisible here by 11, because if we take 11 multiplied by some whole number, we should get 23 to the k minus 1. Now, our p of k plus 1 is going to look very similar, but instead it's going to be a different whole number, so we'll call that W2. That's equal to 23 to the k plus 1 minus 1. And now we'll work on our p of k to try to make this look like this. So let's work on the right-hand side. Now we want to match exponents here, so we're going to use that trick again. So I'm going to multiply everything here by 23 on both sides. So now I have 23 multiplied by 23 to the k minus 23 is equal to 23 times 11 times W1, so that's 253 times W1. Okay, now on the right-hand side, this is just 23 to the k plus 1 minus 23. So I have 253 W1 here. All right, now the right-hand side is getting close to looking like the right-hand side over here, but notice that they are differing by a positive 22. So what I'm going to do is add 22 to both sides here. Now when I add 22 to both sides, I'm left with 23 to the k plus 1 minus 1, and on the left-hand side, I have 253 W1 plus 22. So just to recap, I added 22 to force it to look like the right-hand side. Okay, so to match the right-hand side, which is here. Okay. All right, now when I look at this, I'm going to factor out an 11. Remember, 11 times 23 gave me that 253. So I have 11 times 23 W1, so some whole number times 23 plus another whole number is equal to 23 to the k plus 1 minus 1. Now, this is where you have to remember that you want the left-hand side to look the same as here, okay, and we're pretty close. So that's the trick here, is just to factor out your 11 first. But now taking a look at 23 times W1 plus 2, well, this has to be a whole number also. So because it's just a whole number, you're going to replace it. So it's a new whole number, let's call it W2. So we have 11 times some new whole number is equal to 23 to the k plus 1 minus 1. Now if you notice, this is exactly what our statement p of k plus 1 says. So therefore, p of k plus 1 is true. And therefore, p of n is true for all n. Let's practice one more statement about factors so that you're more comfortable with this. So here we want to start with our base step. And so we have 2 to the second power minus 1, which is equal to 3, is in fact divisible by 3. So let's try our inductive step now. We are going to assume that p of k is true, and we want to show that p of k plus 1 is true. So writing out our p of k, we have 2 to the 2k minus 1 is equal to 3 times some whole number. Okay? So this is the trick to make sure that you can write this as an equation. Now our P of k plus 1 statement will be 3 times some other new whole number is equal to 2 to the 2 times k plus 1, which is just 2k plus 2. So I'm going to erase that and write that as 2k plus 2 minus 1. All right, now we're going to work on the left side here, this p of k, to make it look like p of k plus 1. And I'm going to start by choosing the exponent side. So if I look at this, this is differing by this, a plus 2 here in the exponent. So instead of just multiplying by just a 2, I'm actually going to multiply by 4, 2 squared. If I multiply by 2 squared here on both sides, now I have 2 to the 2k plus 2 minus 2 squared, which is 4, equaling on the left-hand side 4 times 3, 12 times w1. Okay, so this is a little bit of a trickier part here, is to make sure you match the exponents correctly. So we had to multiply by 2 squared here instead of just 2. And now from here, since my right-hand side is looking pretty close, but I notice that it's differing here because I have minus 1 and over here I have minus 4. So I'm going to add 3 to both sides here. Okay, now I'm left with 12 times w1 plus 3 equaling 2 to the 2k plus 2 minus 1. Now my right-hand side match. Okay, both right-hand sides are good. Okay, now I'm going to work on the left. Well, on the left-hand side, I am just going to factor out a 3 here. So I have 3 times 4w plus 1, and that's equal to 2 to the 2k plus 2 minus 1. Now, this is again the same reasoning that we used before. If we take a look at this, 4w plus 1 is simply another whole number. So because it's another whole number, we can simply replace it with a new whole number, and we'll call that w2. So now I have 3 times w2 is equal to 2 to the 2k plus 2 minus 1. If I notice, that does match here with my p of k plus 1. So I'm going to write, since p of k plus 1 is true, p of n is true for all n. All right, that's the end of the lesson. Tomorrow in class we'll take a look and work on some more problems. Nice job.